So, good morning, good afternoon, everybody. I think that we are everywhere, all around the world. So it's time to start. I think we are 40 people here. People will be coming little by little. So it's time to start the session of today. And the first talk of this session will be delivered by Dr. Oleg Denisov, and he will talk us. I mean, the title is Perceiving the Emergence of Hadron Mass through Amber and CERN SPS. So Oleg, please, you can share your screen with us. I think that everything has been checked. So
okay, very good. Yeah. So hello, everybody. Just tell me whether I have to go to the full screen mode or it is better like this.
Very good. It's working. So you can go ahead.
Okay, so thanks a lot to organizers for giving me possibility to invite me and giving me a possibility to share with you our ideas on how we can perceive the emergence of Hadron Mass through the Amber facility as CERN SPS. So this is outline of my talk, very short introduction, then basically I will concentrate on the emergence of Hadron Mass and how we can access this phenomenon or shed light on this phenomenon using our methods available for us, and then a couple of new ideas, timelines, and short summary. So the Amber, it is a newly approved experiment at CERN, and we have started to work on the program of this facility more than 10 years ago. There was a number of workshops, and in the end, the effort was somehow summarized by the submission of the letter of intent, which we submit to our committee in the January of 2019. And as I said, Amber stands for the apparatus for Muson and Barian experimental research. It is not a single measurement experiment or not a single program experiment. This is a facility which comprise the universal spectrometer, various kind of beams, and we can together with these beams we can use various type of targets. So while we were discussing what is the most interesting and important things we can do with this facility, we came up to this list of experiments, which can naturally be split into two parts. First part, sort of our near future. This is those experiments we can run profiting of already existing beams delivered to our experimental area. And the second bunch of experiments or measurements we can do once CERN make us available a so-called RF-separated high-intensity kaon and antiproton beams. And just to stay very short, basically our standard hadron minus beam, dominated by the pions, it is 97% roughly. And then there is a very small percent of K minuses and antiprotons. So the basic idea of this technique is to remove using sort of relativistic spectrometer this pion component from the beam and extract to the experiment only kaons and antiprotons. Doing like this, you can really increase the intensity of the extracted kaon and antiproton beam. So once we have submitted letter of intent, we got a positive reaction. So we decide that we go right away with the submission of the proposal, which is the next step compared to the letter of intent. And we decide to put on this proposal 3 experiments from our program for the conventional so-called beams. This is a proton radius measurement experiment. The experiment where we are going to measure the anti-proton production cross-section in the proton-helium interactions, and a Drell-Yan experiment with the pi minus and pi plus beams. So this phase one proposal was submitted in September 2019, and it was approved in December 2020. So these three measurements we have basically on the pocket, and we are going to do them in the period from 2021, 2022 to 2027. It is longer time than we asked for because we have other experiments on our line, and there will be as well a long shutdown, which will cost us 1 year of running time. And in parallel, we are working, of course, on the phase two proposal, and we are going to submit it in the end of this year, beginning of the next one. And this proposal will cover physics we can do with the RF-separated high-intensity CERN and anti-proton beams. We think right now that there is one sort of joining feature of all this, or many of those measurements we are proposing in the our letter of intent and the proposal. And this physics issue or physics phenomenon is emergence of Hadron Mass. We really consider emergence of the Hadron Mass to be a main bearing column of the whole amber. And just to remind you, you certainly know all this, but I would just remind you that that was great thing, a discovery of Higgs boson. But to some extent, it is useless in trying to understand from where basically all visible matter, mass of the all visible matter appeared, emerged, because the Higgs mechanism explains very small percent of the visible, of the mass of the visible universe. And this is not all, because you know, looking, for example, at pi and proton, they are so similar. They are composite objects. One consists of two light quarks, another consists of three. So they are basically the same, but from where this difference in the mass is appearing? Why pi so unnaturally light and proton so heavy? Certainly, this cannot be explained by Higgs mechanism. So we have to dig in the QCD. And this is not only about the final numbers, say, but the dynamics of the both objects, pi and proton, because we know that in the chiral limit, basically the mass of the proton remains the same, but if we are talking about the Goldstone bosons, pi and CERN, they by definition have to be massless. So something inside inside dynamics of these three objects are sort of very different. And in order to understand why and how, we have certainly to study not only proton, which is probably the most well-studied and known object, but as well pions and CERNs, which are much more difficult to study because they're unstable. So talking about the main questions we have to answer running our experimental program, I should anticipate that we are preparing together with Craig Roberts and colleagues the list of science questions. But here I want to just to bring you in grosso modo to three issues. Questions to be answered, or at least partially answered, or to be looked at. This is first, as I already said, the mass difference between pion, CERN, and proton. Why it is this? Second, what generates this difference in the mass? Certainly this is not Higgs, but there might be, should be interplay between Higgs mechanism and the emergent mass mechanism. And the question to my mind a little bit apart, it is about the gluon content. Because we know that basically the gluons which creates the mass of these objects, or gluon quark interactions and gluons. So this is a physics issue we wanted to address, and we can do this in different ways. And here I put a list of some methods we are going to use as experimentalists in order to access one or another physics quantity. And this is a Drell-Yan process, very well Drell-Yan process, the quark anti-quark annihilation with the production of the leptonic pair, dilepton pair, from photon production as well, Chermonia production, and pi and k diffractive scattering. This is the issue which we are still studying. Talking about the Drell-Yan measurement with the pi plus and pi minus beam, as I said, it is already approved part of the program. And why we are unique here? We are unique here because of very simple reason. The previous experiments were done very long time ago. It was Na3 and E615, and they had much smaller statistics compared to what we intend to have. So since then, our understanding of the whole thing is developed by much, so we need new data. Because you cannot even reanalyze in certain aspects the data by E615 and Na3. So, and here in this table, I just put the numbers. So the statistics which were accumulated by E615 and Na3, running with a pi plus and pi minus beam, and compare it what we expect to have. And why it is important to have both pi minus and pi plus? Because only doing these two different Drell-Yan experiment, you can separate the valence quark contribution from the C quark contribution. And this is exactly what we have to know, or what we want to know, if we are talking about the internal pi or KEN structure. And as an illustration of our sensitivity, I put here the differential cross-section in red points as we expected to have it in amber, compared to the black points from Na3, and this is differential cross-section, Drell-Yan cross-section induced by positive pi-n beam. So you see how better we will do this measurement. And why it is important, as I said, just by simple combinatorics, combining the result of two measurements, you can access directly or valence quark distribution or content or C quark content. And this is our sensitivity and how we would be able to distinguish between different models, which, the modeling the different ratio between the different percent of C quark compared to the valence quark. This is concerning pions, but certainly, as I said, we have to study not only pion but as well KEN internal structure. And for KEN, it is even worse, and the experimental situation even worse, because the worldwide statistics on the internal KEN structure, it is 700 K minus induced Drell-Yan events. So you can count them by the fingers on one hand. And this is exactly what so this, the experiment we will do in the next years for pions. We wanted to compare as well with the KEN beams, KEN minus and KEN plus beams, in order exactly to do the same job for KEN as for pion, to measure and separate the valence quark and the C quark contributions. And so far, as I said, the worldwide statistic is 700 events, and this is a ratio between the U-quark distribution in Keon and in Pine, as it was measured by an S3. And this large error bars, it is their data, and these small statistical bars is what we expect to have in AMBA. So for the same final state as Drelian, so 2 leptons in the final state, there is another thing which we will do. It is certainly a Chermonia production. So why Chermonia is important? Because it is sort of more difficult to analyze process compared to Drelian, because there are 2 competing processes inside, the bar annihilation and gluon-gluon fusion. But it is sort of maybe richer to some extent a process, because you can really test the different models which describe the different percent in these 2 processes, like collaboration model or non-relativistic QCD approach. And even more important, using these Pi-induced J-psi data, you can have, and it was illustrated in this very recent paper by Zhen Chipeng, Wenchen Chang, and colleagues, published in the end of the March. It is illustrated how you can use the non-relativistic QCD approach in order to extract gluon content of Pine from the J-psi Pine-induced production. This is exactly what we wanted to do. And of course, psi prime would be very interesting to observe and to study, because there is no feed-down effect from compared to the J-psi signal. Talking about statistics, we expect it is really huge, because this is a factor of roughly 40 compared to our statistics we will have in Drelian. And so with these statistics, we can really help to distinguish between, or to make better parameterization of the PDFs. And for example, this is on the bottom plot. You can hardly see our error bars, compare it to the 2 different parameterizations. So also resolving power of this measurement will be very high. There is alternative method how we can measure or study the gluon content of the Keon in this very case. This is a so-called prompt photon production. We know that basically for the moment we have no information at all about the gluon content in Keon. And according to the Eisenschwinger equation, we should expect factor 6 smaller contribution from gluon to the compared to Pi, and this we have to measure. This we have to verify. And basically, we propose to do this measurement with the Keon-induced photon production, measuring basically an isolated photon in the final state. We have very good coverage, colorimetry coverage, electromagnetic colorimetry coverage of the spectrometer. And this is important because for the prompt photon production, the background is very high. So in order to see signal over the background by a reasonable factor, we have to cut on a very large PT. So we have to have a full coverage of the acceptance of our spectrometer by electromagnetic colorimeter, and this is exactly what we have. Hadron spectroscopy. It was naively clear that it is issue or the physics which is tightly related to the emergence of Hadron Mass phenomenon. And we learn from Craig Roberts and his colleagues, it is really so. And the very important for the emergence of Hadron Mass to precisely know all spectra of the excited light quarks and the excited states in the Keon sector. And if for the light quarks, non-stretch quark, we are doing now the job with COMPASS because we have roughly 10 to 100 times higher statistics compared to what has been collected so far, and we will do our job there. The situation is much worse for Keon sector because basically since 30 years there is no activity there. The spectras are really poorly known, poorly established. Only 12 chaonic states is confirmed in the summary table. 13 needs to be confirmed. Many predicted quark model states, bi-quark model states are missing. And the basically most PDG entries, they are 30 years old. And this is why we think it is extremely important to go ahead with the business we have already started in COMPASS, because we have small statistics of the diffractive scattering events in a Keon beam. We intend using high intensity Keon beam in amber to basically improve our statistics by a factor of 50. And this would really allow us to rewrite the Keon sector of the PDG. And this is, as we understood, is extremely important input information for the emergence of Hadron Mass. Proton radius puzzle, you know that there is this long-standing problem that whether it is measured in one way or another, proton radius appear to be different. There is a set of experiments in the spectroscopy, in the EP, MUP spectroscopy, and the number of experiments and the scattering experiments in the EP scattering. The data which are missing for complexity, for completeness, sorry, it is muon proton scattering. And here we know that this experiment planned by Muse at PSI, and we as well propose a different muon scattering experiment with amber, because it is high momenta muon scattering. Muse, it is very low momenta muon beam scattered. It is not even clean beam, and there is basically everything. We have 150 GeV muon beam with basically no admixture of other species in the beam. And why it is important to have this measurement in the high energy, with a high energy muon beam? Simply because of this very simple formula. So you have to measure basically what gives you proton radius. This is the electric form factor, which stays here, which is proportional, which is sort of and coefficient in front of this form factor is epsilon. And but there is a problem, because while you are doing measurement, normally you are as well sensitive to the magnetic form factor. And in order to cancel or to reduce systematics in your measurement by reducing your sensitivity to the magnetic form factor, you exactly have to go in the very small Q-square range, because the tau, which is coefficient in front of the magnetic form factor, will be smaller. And if you go up with energy, the epsilon will be higher. So very small q square, high momenta of the incoming particle. This is exactly type of experiment you have to do in order to reduce systematic error and the contribution from the magnetic form factor.
Oleg, you have 5 minutes left.
Yes, yes, yeah. So I will probably nearly skip the contribution which we are going to do in the spin program, because it was widely addressed by the compass. I would just to say that we intend to do the polarized Drell-Yan, the polarized DVCS measurement and polarized Drell-Yan, because, well, for Drell-Yan, still you know that there is an issue of the sign change from CDS to Drell-Yan. This factorization, so factorization in TMDs are not yet experimentally confirmed in spite of effort by Compass, STAR, and so we wait for results from SpinQuest. And in case still there is an open question, we will do this anti-proton induced Drell-Yan experiment. Concerning new ideas, this was somehow the one in the discussion with Craig Roberts, and what Craig Roberts says that the pi and Can distribution amplitudes DAs nearest thing in the quantum field theory to Schrödinger wave function, consequently fundamental to understand pi and Can structure. Model theory prediction for emergence of hadron mass is expected in next dependence of pi and Can DAs, and this is exactly what is shown on this left plot, where you expect the different the curve shape, whether the EHM mechanism is dominant or the Higgs mechanism is dominant. And actually, there was only one measurement done so far who can access this kind of physics values. It is E691 with 500, so it is dijet events and 500 GeV induced by 500 GeV pi minus beam. We trying to examine and to understand whether we can do similar thing, even if we have a smaller momentum of the incoming beam. So we rather will observe the separate hadrons in the final state. And concerning the meson radius, again, I quote Craig here, the precise measurement of pi and Can radii will reveal the compositeness or confinement scale of the near Goldstone bosons. And compared to the proton radius data, you see that there were many experiments, a lot of data about the pi radii and Can radii. We knew basically nothing or very few. And this is certainly experiment we intend to run as well in AMBER. So this will bring me nearly to the end. So as I said, the AMBER phase 1 proposal has been submitted and approved. And what concerning the running plan, it looks like that. So we will start next year with a proton radius measurement, and it will take us roughly 1 year. Then we will do short measurement for the antiproton production cross-section. And then we continue for 2 years with the pi-induced Drell-Yan. And this is how the AMBER sort of program looks on time together with the different other programs which intend to shed light on the EHM phenomenon on the sort of worldwide scale. So we intend to finish phase 1 by 2027, 2028, and then we will be given RF separated beam and we will continue.
Look, you are running out of time.
Yes, so this is my summary. A wide and extremely competitive physics program brought together strong interest in the hadron physics community. This is about AMBER. Main bearing column of the AMBER is emergence of the hadron mass phenomenon. Our knowledge on pi and structure will be much improved after phase 1, and we hope and we are pretty sure we will do great job as well for Cairns during phase 2. Thanks a lot.
Thank you for this very nice talk covering the perspective for CERN. Adam, please.
Yes, hi. Thanks, Oleg, for a very nice overview. So from the table, I saw that the lowest energy for the kaons is around 50 GeV. Can you go lower than that?
Yes, we can, but there we are only limited by the optics of our line, and the issue is different. We were always trying to push CERN to go higher because for hadron spectroscopy, you know, there are two blocks of the program with kaons, with high intensity kaon beam. This is spectroscopy and Primakov, and they are not extremely challenging neither from because it is hard to go high in the moment of the RF separated beams because of the organization of the beam line. It is easy to go lower, but our goal was exactly for the Drell-Yan experiment to push to the maximum the momenta and intensity of the kaon beam. So this is why this was a critical issue for us. As we can run hadron spectroscopy with much smaller beam intensity, I think we have a lot of freedom there. But what
the reason I'm asking is because if you go lower, you're really reaching a much more sensitivity to other production processes. And of course, you can do charge exchange, and that opens a whole new area for spectroscopy.
In principle, we can do this, but what kind of energy you are talking about, Adam?
Well, I'm talking about going down to something like 10 GeV.
Well, 10, it is difficult because 10 you will have very slow.
I mean, basically, you want to leave the diffractive regime and, and go down to where you start exchanging charge and strangeness.
This we have to evaluate, because if you reduce by a factor of 10 the moment of kaons, you will have 10 times more kaons decayed before a kaon reach your spectrometer. So in this case, if we are talking about say 30 or 40 GeV, no problem. If you go to 10, then we have to talk to our beam people. They might be able to estimate what kind of beam intensity we will have in the end, because you know it is not a critical issue for spectroscopy, because we intend to have something like 10 to the 7 per second kaons per second for Drell-Yan, but normally spectroscopy program we run with the order of magnitude lower beam intensity, because we cannot digest otherwise. Otherwise our spectrometer became blind.
Well, so hopefully something we can explore in the future.
This is certainly what we can discuss with machine people. Yeah.
Great, thank you.
Are there any other questions? I don't see any other raised hands, so I think if no one. Okay, so I think
I could come with one question, Paul Hoyer.
Okay, Paul,
could you say something about the choice of target? You have only carbon, I understand.
Well, we actually have not only carbon, but we have as well tungsten. We have 3 carbon cells and 1 tungsten cell. The choice of carbon is very simple, just because of the same number of protons and neutrons.
Okay, very good. Thank you.
Mm-hmm.
Okay, thank you again, Oleg, and